Today I'm going to talk about the spatiotemporal diversity of the Atlantic Nino and the associated rainfall variability over the West Africa and South America. So this work was led by Ignacy. He was a student intern from Spain. He was here at AOML in the summer of 2018. And then this work, my talk here today is based on a new paper that was published in a geophysical research letter a couple of months ago. And the co-author of that paper include myself, Senki Lee, Greg Falls, and Jose Pellegrini. And Jose is Ignacy's PhD supervisor. So here is the outline of my talk. Toward the end of my talk, I'll talk about why NOAA should care about the Atlantic Nino and its diversity, and then I'll open up for more discussion with all of you. So what is Atlantic Nino? So what's shown here is the composite map of the 22 Atlantic Nino events. So this is Equatorial Atlantic SST anomalies, average between 3 degree south to 3 degree north for the entire Equatorial Atlantic from 30 degree west to 10 degree east from January to the December. So you can see that this composite map shows that Atlantic Nino usually develops in spring, peaks in summer, and dissipate during the fall. And as you can see from this next plot, Atlantic Nino is characterized by the warm sea surface temperature anomaly, and then a depressed or a deeper thermocline in the eastern Equatorial Atlantic, and then uplifted thermocline and the westerly wind anomaly in the western basin. And some of these Atlantic Nino events are linked to increased frequency of the heavy rainfall and floodings over these countries in the West Africa, neighboring the Gulf of Guinea here. And then increased rainfall over the northeastern South American region as well. And then also links to Atlantic Niños, also links to the reduced rainfall of the Sahel region. So it's a links to the reduction or the failure of the West African summer monsoon. So this is a Hubble diagram for the 22 Atlantic Nino events that we have identified from 1949 to 2019. And you can see that the time, they're very different. Each events are very different. And then timing of the onset and the amplitude of the peak and the timing of the dissipation, they are all different. And also the zonal extent of this anomaly are very different. So it's really difficult to find any two events that are very close to each other. And then I show you in the previous slide the composite map of these all 22 events, but you can definitely see from these figures that the composite mean really does not really describe the Atlantic Nino pretty well. So we need to look into the diversity of the Atlantic Nino. So this is methodology, so it's very descriptive, but I got to go through it. So in order to objectively identify the preferred mode of the observed Atlantic Nino events, we carried out a UF analysis of this 22 longitude time map of the Equatorial Atlantic SST anomaly, and the resulting principal components associated with each individual Atlantic Nino event, and the EOF, that is map, represent a linearly independent set of the longitude and time maps. So these two leading PCs, principal components, explains about 30% and 24% of the variance. And we rotated this PCs at 90 degree to align some of the observed events align better with the PC components, PC axis. So each of the rotated EOF mode represent two contrasting Atlantic variety or flavors. Oh, I use interchangeably. Sometimes I use a flavor, sometimes I use varieties. It's the same thing here. So that corresponds to adding this EOF pattern to the composite mean and subtracting the EOF from the composite mean. So that lead to four main Atlantic Nino flavors. So we talk about this in more details in our 2020 JADA paper. And also, this method was previously used in our 2014-18 paper that was applied to analyze the diversity of the ENSO in the Pacific. It's the same method. So the first rotated EOF mode distinguished two contrasting flavors, focusing on the decay phase. So the first mode, first flavor, I'm sorry, is characterized by complete termination of the Atlantic Nino around shortly after around August, so that we called it early-terminating flavor. And the second one is characterized by the pretty strong STS anomaly that persists all the way toward the end of the year. So we call this flavor a persistent flavor. Okay, the second rotated EOF distinguished two contrasting flavors, but focusing on the onset phase here. So the third flavor is characterized by the very early onset of the warm SST anomaly in January or even earlier, and gradually developing and becoming a very large SST anomaly in the summer. Then it dissipates pretty early. And so we call this early onset flavors. And the last one is it developed pretty suddenly, quite suddenly, and pretty late in June and July. So we call this a late onset flavors. So we have these four Atlantic Nino flavors that I'm going to talk about their impact on the rainfall and the onset mechanism and things like that in the next several slides. And this one is basically show you the 22 Atlantic Nino events as a function of rotated PC1 and PC2. For instance, this one here is a 2019 event. It is characterized as the persistent flavor, or 1991 Nino events is early-terminating flavors, for instance. Okay, so in the next several slides, I'm going to talk about the climate impact of these four flavors on the West African and South American rainfall. So I'm going to show you the time series of the precipitation of this West African regions here between equator to 10° north from 20 west to 20° east. But I'm showing only the land precipitation. So the precipitation over ocean are not included, only the land precipitation over here. And then I'm going to show you also the precipitation over this sector, South American sector, between equator to 10° north. So I'm going to show you the two time series here. Okay, let's talk about the first one, early-terminating flavor. So in this case, the Atlantic Nino anomaly terminated pretty early. So the consistent with this warm anomaly here, the West African rainfall. Oh, by the way, I'm sorry. This green here is the West African anomaly, rainfall anomaly. And then orange color here is for the South American rainfall anomaly on those boxes that I showed you in the previous slide. So you can see that for the West African rainfall is enhanced for a very short period of time from July to August, just 2 months. And then for the South American rainfall is also enhanced during those time, but it persists slightly longer. So that they are more or less consistent with the SST pattern. However, if you look into the rainfall over the South American region, there is a big reduction in April, May, and which definitely cannot be explained by the SST anomaly. And I'm going to show you and discuss later that this is really due to the preconditioning factor or external forcing factor that is driving this Atlantic Nino flavor. So there's external factors involved there. Okay, next one is persistent flavor. So consistent with this persistent SST throughout the entire year, rest of the year here, the West African rainfall is enhanced for the extended period of time from July to October. And the South American rainfall is not very much enhanced in the peak summertime, but later it is enhanced throughout the end of the year from September to December. So they are more or less consistent with this SST patterns. However, again, there is a reduction of the South American rainfall before the peak time of this Atlantic Nino flavor. So this is definitely nothing to do with Atlantic Nino, this Atlantic Nino. So we're going to show you later that this is again is due to the external forcing. We'll talk about it later. The next one is Early-Onset flavor. So in this case, what is surprising is that this early development of the SS anomaly in this case does not really translate it into the enhanced rainfall of the West African region. It's pretty much neutral during this time. And then so that this flavor terminate pretty early, that its impact on the West African rainfall is pretty much limited to July to August. So and then, but then after it dissipated, the South American rainfall was increased from September and December. And again, this is not due to the Atlantic Nino, of course, and also the rainfall in the South American region again are reduced during this onset phase, and that again is due to the external factor we'll talk about in that later slide. Okay, so the last one is the late onset flavor. In this case, the Atlantic Nino appears pretty suddenly in June and July and persists longer. So consistent with this SS pattern, West African rainfall is enhanced for extended period of time from July to October. And then very interesting thing is that the South American rainfall is not affected all throughout this year by this Atlantic Nino flavor, and that's very interesting. Okay, let's talk about briefly about the West Africa monsoon. So this is Sahara region, let's say 10-degree north to 20-degree north. Let me just check whether everybody's here because I may be just talking to myself. Okay, looks like I'm talking to everybody. Good. So I'll keep on talking. Okay. So this is Sahara rainfall from 10-degree north to 20-degree north is pretty much reduced during the Atlantic Nino events, and that we know from the earlier mini studies. So Sahara region is a kind of it's a basically a desert, so it received the rainfall for only for very limited time around August or so. So the failure of the monsoon, West African monsoon, due to the Atlantic Nino has a large impact on the ecosystem over there, over the Sahara region. And then you can see that, what I'm showing you here is basically West African rainfall over the land that is as a function of latitude. So there is very little land masses in the southern hemisphere, so that's why you don't see much of a variability. In the northern hemisphere, so this is average between 20-degree west to 20-degree east. So only the land precipitation anomaly. So you can see that for the persistent and late onset flavor, the reduction of the sour rainfall is pretty much robust in these two cases, but early onset phase flavors, the impact is pretty much negligible. So there's some diversity in that aspect as well. Yep. It's not moving. Okay, nice. Now let's talk about the onset mechanism. This is pretty much a preliminary analysis for the onset mechanism. So it's not a quantitative heat budget analysis. This is a descriptive analysis. Just want to let you know that before I start. So for the early-terminating varieties, so these are basically the maps of the surface wind anomaly as vectors and sea surface height anomaly as a proxy for thermocline depth for the as a contour. So green means a positive value, so it's a suppressed thermocline, and then the sky blue means uplifted thermocline. And then this SST is shown as a shade. So you can definitely see that there is a development of the cold anomaly in the tropical North Atlantic and a warm anomaly in the tropical South Atlantic in the springtime. And consistent with this strong cross-equatorial SST gradient, there has to be interhemispheric surface wind develops here, and that seems to initiate this Bjerknes feedback, presumably a Bjerknes feedback that drives the movement of the water so there's a piling of the upper thermocline water, surface water, I'm sorry, and then and the increased SST here. So that become a full-blown Atlantic Nino in JJA. So it's definitely this one. We can say that it's safe to say that it's driven by a negative phase of the Atlantic Meridional mode AMM and during the Boreal Spring. And this mechanism was suggested earlier by Greg Foltz and McFadden in 2010. So this is consistent with the study. The next flavor is a persistent flavor. So this one is very, very tricky, and we only have a hypothesis, one hypothesis, but it may not be correct. So this is a very tricky situation here. So because if you look at the what happened along the equator, there is a very little precursor here. In the equatorial region. Instead, you see there's a strong reduction of the westerly in the off-equatorial easterlies, in the tropical North Atlantic and tropical South Atlantic, pretty robust signal. So that reduce the latent cooling, so that will warm up this off-equatorial tropical Atlantic SST in both hemispheres. And additionally, due to this southwesterly wind anomaly, there is anomalous coastal downwelling of the coast of the West Africa, and that seems to create accumulation of the warm water volume. And I think in some literature they call this Dakar El Nino also. So anyway, so the Rikito et al. 2012 suggested that this accumulation of the warm water volume can be later transported, advected to the equator by the ocean current, and through the Bjerknes feedback, that could create a big Atlantic Nino events, such as what you see here. So it seems like that seems to be the only explanation for this flavor. So we're glad that we found this paper, but we like to study more later with a heat budget analysis to confirm this hypothesis. Okay, the next one is the early-onset flavor. Early-onset flavor. So in this case, you can see that during the winter and the spring, there's a persistent cross-hemispheric wind, and that seems to be the one that a main mechanism that triggered this Atlantic Nino and accumulation of this warm water volume to the eastern basin here. So in that sense, this Atlantic Nino flavor is similar to the early-terminating cases here, early-terminating flavor. But one big difference is that there is no cold assist anomaly in the tropical North Atlantic. So it's really difficult to say that, and this is really AMM mode. So instead, we think that this persistent cross-hemispheric wind is forced by something else, forced by external factors. So we're going to talk about that in the later slide. So it's externally forced cases. That's what we think. Okay, the last one is the late onset flavor. In this case, there is no external preconditioning in winter or the spring along the equator. There is very little preconditioning factor, but then suddenly in JJA we have a large Atlantic Nino develops here. So because we don't see much of a preconditioning or external forcing, we think that it is driven by the atmosphere-ocean processes internal to the equatorial Atlantic. So we think that is kind of self-sustained oscillation, pretty much similar to the El Nino, many cases, the canonical El Nino in the Pacific. And you can also see that there is a weak buildup of the thermocline water in the Western Basin, and we think that that is later propagate with the help of the okay, so Renata says comments. So I'll get back to it a little later. So that could initiate this Atlantic Nino pattern. So we think that this is a self-sustained internal oscillation. Okay, let's talk about the impact of ENSO on the onset of this variability. So this is basically the same as the Holt-Miller diagram of the full flavor that I showed you earlier. Here for the Atlantic Nino flavor, but I extended the domain, time domain, extended 6 months afterwards and 6 months prior to it. And also its entire time period is now 2 years. And then also extended the spatial domain to the Pacific, Central Pacific to Eastern Pacific. So you can see the what happened in the Pacific Ocean as well. So you can definitely see that for the persistent and early onset flavors, there are links to the very strong Atlantic Nino events during the preceding boreal winter season. So we think that these two flavors are externally forced by the El Nino. It's pretty interesting that after the onset, after the peak of the this El Nino Atlantic Nino flavors, there is a La Nina popping up here. Maybe there is some connection, but that is kind of beyond the scope of the study. So that's we didn't really pursue further. Another thing that is interesting in this figure is the early-terminating flavor. You can see that definitely there is cold anomaly. So in the Pacific, so it's kind of suggesting La Nina patterns in the preceding winter, but the amplitude is pretty small, even smaller than the Atlantic Nino itself. So this connection is pretty weak. However, so what it suggests is this. What it suggests is that occasionally, not all the time, but sometimes these La Nina events in the winter can lead to the AMM, a negative phase of AMM in the Pacific. So cold SST in the north and south, warm SST in the south, in the Atlantic, and that happens quite often. But we know that Atlantic meridional mode is also self-sustained oscillation, and also is forced by other factors. So they do not always project it to each other. so slow network connection. So I just got the warning that the connection is not good. So I'm gonna turn off the webcam. Oh, it is turned off. Oh, okay. All right. I'll just go ahead. Okay, so that's it. And then the last flavor for the late onset flavor, you see there is a very little connection to the Pacific. So that's consistent with our conclusion that a late onset flavor is basically a self-sustained oscillation internal to the Atlantic basin. Yeah, I think I'm almost done. So this is a summary. Now we have 3 key points. So the systematic statistical analysis identified 4 most frequently occurring Atlantic Nino flavors during 1948 to 2019, and they are early-terminating, persistent, early-onset, and late-onset flavors. And due to the differences in the timing of the onset and the dissipation, they display the large differences in rainfall over West Africa and South America. And most of the flavors are preconditioned by the cold tropical North Atlantic in the cases of the early-terminating flavor, or El Nino in the cases of the persistent and early onset flavors, except for one flavor that is a late onset flavors. In that case, there is no clear external forcing that drives it. And I want to add 2 more points. First one is that this persistent and late onset flavors corresponds to, yeah, Molly has it right. Corresponds to an extended period of the increased rainfall of the West Africa from June to October. So we know that June to October is also the hurricane season. And early-terminating and early-onset flavors correspond to a very limited period of the increased rainfall of the West Africa, just for 2 months, July and August. And for the South American region, the rainfall variability associated with these flavors are more or less consistent, but much more complex. Especially, I want to point out that the South American rainfall prior to or after the peak season is largely driven by either the AMM. In the case of the Atlantic Meridional mode, in the case of early-terminating flavor, and ENSO for the ENSO in the Pacific for the cases of the persistent and early onset flavors. That's it. And then I just want to add 2 more. I have a 2 more slide. Okay, so this is slide. So this slide is mainly why I said in the beginning why NOAA should care about the Atlantic Nino and its diversity. So what I'm showing you here is a number of tropical storms for the positive AMM mode and negative AMM mode, and this is for the La Nina and for the El Nino, and this is for the Atlantic Nino and for the Atlantic Nina. So this is ongoing research that Dongmin is working on, and I think he's almost done with the analysis, and he look at the model simulation. I think he also did some model simulation, carried out AGSCM simulation too. So all this, his analysis suggests that there is a significant link between Atlantic Nino and the named tropical storm generated over the tropical North Atlantic east of the 60° west. So we're talking about tropical storm formed east of the Caribbean Sea. And we already started the discussion with the HLD, GUS, and also CPC with the Kaihon. So ultimate goal of our work is to develop additional predictor for the seasonal hurricane outlook. For instance, for the seasons when Pacific El Nino situation is kind of neutral and we don't have AMM in the Atlantic, and that in that case Atlantic Nino could be a very important predictors for the Atlantic for the hurricane. And then another thing that I like to talk to you about is that I like to create a web page at AOML or a PHOD or CMIS to update, provide a historical Atlantic Nino and Nina episode. So I like to update it every 3 months to provide the indices for the community. If you're familiar with the CPC ENSO website, this is exactly the format they use. So by the way, this is Atlantic Nino. This is Atlantic Nino. So I updated until the end of the last year. So I want to keep on updating and there too. We used exactly the same methodology to remove the trend that CPC is using. So that's another plan that I have. And then this work is based on this paper published earlier this year in the Geophysical Research Letter. Okay, thank you very much for your attention.